Welcome back to Dynamic Systems and Control. So today we review the previous material and learn some tools, complex number and Laplace transform. So the dynamic system is a system that evolves with time, a system that the previous input influences the current output. Examples can be a car, or a mass, or a heater. And by doing control, we want to make a system that ensures desirable properties. So actually, control can be both open loop and closed loop. And open loop just gives a command and doesn't monitor the output. Closed loop system monitor the output. So feedback control systems tries to maintain prescribed relationship of one system variable to another, such as torque, such as velocity of a car. So controller compares the output and the reference and decide the control input to a system. Therefore, the plant can generate desired output. So this system feedback the plant output. Therefore, that's why it's called the feedback control system. Versus open loop system doesn't get feedback. It has just one-way route. So yeah, it doesn't correct its control action depending on the plant output. So that is an open loop system. Also, feedback control system is known as closed loop control system. So it has closed loop. So therefore, it is called closed loop control systems. So there are 4 components of this feedback control system. Plant, it's being controlled, such as a car, actuator, which drives the plant to do something, such as a motor. Sensor senses the output of the plant, such as a velocity sensor or torque sensor. Controller compares the output and to the reference and decide the control action. And there are also signals such as reference, what you want to the output to be, such as desired speed, desired torque, or desired angle. And disturbance is forces and torques that affect the plant, that influences plant dynamics. So for example, if there's a car moving in this direction, the wind can be a disturbance to this car because it influences car dynamics, or the road condition can be the disturbance of this system. Noise is a random signal that corrupts the measurement output. So disturbance influences the plant. Oops. Plant dynamics, and noise influences most likely sensor Well, disturbance also can influence the actuator, but we typically talk about the plant. So through this course, after this course, you will learn how to design a controller for a system. To do so, you will learn how to model the dynamics of the system and how to analyze the system, and eventually how to design a system controller. To do so, you will, in this course, we use some tools such as complex number and Laplace transform. So today, we will review the tools, complex number and the Laplace transform. So what is a complex number? The complex number is a number which has two components, which is real part and imaginary part. So real part, imaginary part. So it can be expressed in the complex plane. And A and B are real number, and Z squared becomes -1. Mathematically, the benefit of having this complex number is that this complex number allows a solution that have no solution in real numbers, such as this equation. You can't solve in real numbers. But if you adopt this concept, J squared equals -1, it becomes x plus 1 squared becomes plus minus 3 squared and J squared. Then next thing is take root, then it becomes x plus 1 equals plus minus 3 j. Then x becomes -1 plus minus 3j. So we can have a solution for this case. And if you want to learn more about the basics or review the basics of the complex numbers, you can go to this Khan Academy. It has good tutorial, so therefore it will help you to remember what you learned before. Okay, so for our case, why do we use complex number in the beginning? It's because there's a reason that I included this mass spring damper system. Why? It's because it's much easier to describe the system behavior if we use this complex number. So let's think about these cases. So for this case, there's a pure oscillation. Looks like sine wave or cosine wave. Okay. So for some controller, it looks like this. But if we tune the controller, it may look like this. There's still some oscillation, but it decays in time, and eventually it almost stops. Another case is that it doesn't oscillate at all. So how do we express those behavior mathematically? So recap, there was a spring and mass. And in the beginning, it was an empty cylinder. And in the beginning, this mass behaves something like number 1. Then, once this is filled with something like water, it behaves something like number 2. And once it fills with something like oil, it behaves something like number 3. So of course, you can express using these complex equations. But is there any way we can express this behavior more compact way, more intuitive way? So therefore, you can design a controller eventually. So for note, in the future, when you design a controller, you may see all these 3 behaviors depending on how to design a controller. So then, like we want to have something to show this behavior in a compact way, in an easy way. So that's why the complex number comes in. So this pure oscillation can be expressed using only this imaginary axis. And this pure damping without any oscillation can be expressed using only real axis. Something like this very complicated one has both real axis because it decays in time, also imaginary axis because it oscillates. So using this complex number, it's easy to express this behavior. And later we learned that even we can say the person put about this F can be considered as input. And then we are looking at output, this oscillatory behavior. And the system itself can be described very simply using this complex number. So that's why you are using this complex number. So then the next step is let's look at quickly review this complex number. So we just look at why we are using complex number. Over here, oops, where's my mouse? And then look at some operations. Okay. So complex number can be expressed as real part and imaginary part. And so this is let's say real part. This is imaginary part. That means that sigma is over here and omega is over here. So let's say this is S, which is sigma plus j omega. It can be also expressed as magnitude and angle. Such as magnitude and the angle, and angle is nothing but arctangent this over this. Omega over sigma. which is imaginary part and the real part. And this can be also expressed as EJ theta. Then there's a called complex conjugate. So let's say S equals sigma plus J omega. Complex conjugate is S star is nothing but sigma minus J omega. So in this complex domain, the sigma is the same, but we have now negative omega. So this will be S star, and this will be theta. So as you can see, the magnitude, therefore, is the same, but the angle is opposite. So therefore, if you multiply those two, this becomes S angle theta times S star angle theta star. This is theta star, and this becomes S star theta plus theta star becomes S square theta minus theta, because this theta star is nothing but negative theta, so it becomes S square. So this is an important property, which is also you will see soon for the multiplication. So if you multiply two complex numbers, you multiply magnitude and add the angles. Addition subtraction is very simple. Let's say S equals X plus JV, X plus JY, and S2 equals V plus J omega. Then the sum becomes just sum the only real axis and the only imaginary axis. So S1 plus S2 becomes X plus V plus J Y plus omega. The subtraction is nothing but S1 plus minus X2, right? So it becomes X minus V plus Y minus omega. So very simple. So multiplication can be, you can use this equation. So again, X equals, this is S1 over here. This is S2 over here. And do some operations. Then after that, you need to simplify and organize equations. You will get something like this, which also can be expressed as magnitude and then angle. In this case, angle is nothing but arctangent, imaginary part, and real part, which is the same as here. The angle is imaginary part and the real part. So this is the multiplication case, but you can be even use a simpler approach. So I not prove anything, but let's say S1 is S1 theta 1, S2 is S2 theta 2. Then the S1, S2 is S1 angle theta 1, S2 angle theta 2. And similar to the operation we did for the complex conjugate, this magnitude can be multiplied and the angle can be simply added, which is S3 theta 3. So the S3, the magnitude is nothing but S1, S2, and theta 3 is the summation of the angle. So this is a very simple operation, which will be very important in the future. When you design a controller, you will use especially this angle approach a lot to design a controller. So this is very important. This is also important, but more importantly, you should remember that for the multiplication, the angle can be simply added. So if you went through until this far, the division is actually very simple. You can also do this approach and then go through other details. But you can also say this is S1 times S2 inverse. So you can say S1 angle theta 1 times S2 inverse angle theta 2, actually, which is the inverse, which is negative theta 2. So what happens is that it becomes S1, S2, theta 1 minus theta 2. So this is just another very important property. So for the division, the magnitude need to be calculated using this method. The angle becomes a simple subtraction. So for example, if there is S1, S2 divided by S4, which is S5, then it becomes S1, S2, S4, and theta 1, theta 2 minus theta 4. So this is one example. So this is fairly simple, but this angle method will be, again, very important in the future. Okay. So we went through this complex number review very quickly, and then we review the Laplace transform. So let's think about why we need Laplace transform in the beginning. Why we don't use the tool we used for other courses? It's because, again, this makes our life easy. Because we are lazy, we want to make it simple. So for maybe spring damper system, you can obtain a differential equation by solving maybe through maybe free body diagram or Lagrangian method or something. You can obtain a differential equation. And by taking Laplace transform, this whole system becomes a separate system with an input and output relationship. And additionally, we can do algebraic equations. You don't need to calculate the complex calculation. It can become algebraic equations. So we can solve for algebraic equations. And another thing is that this system becomes something like plant with input and output, which you saw in a functional block diagram. So it's very easy to design a controller by taking a Laplace transform. And if we need time domain solution, we can always take inverse Laplace transform and get a solution. So two benefits is that we can make a separate entity. Like we can make it like this simple. We can make it a system as a block diagram using a Laplace transform. And you can also make it, you can get on algebraic equations. So like, let's review what was the Laplace transform. So we can change time domain to Laplace domain through these operations. So here is a formal definition. Ft is defined for this, and the magnitude is bounded for some m and sigma, and then this exists, and then you can get a Laplace transform of Ft. So Fs is the Laplace transform of the Ft, and because this whole part is a little bit complicated to write, so again, you are very lazy. So we express everything as L and this bracket. Also, we can take inverse Laplace transform. And then in this case, this is an operator. And we simply write this whole part to A inverse and this. So then let's review some very simple example of Laplace transform. So the simplest one can be a step function, which we look at during the TS session. So step function is defined this is 0, and after 0, it becomes 1. So it means that Ft equals 1 if t is larger than 0. So then Fs becomes and this Ft is 1. So then we can write and it becomes so the Laplace transform of, so let's say this is let's say this we can express as ut, the step function. So Fs of L ut is 1 over s. And let's look at one more example, so called ramp function. So it's the same thing. So we start from this. So again, Fs equals 0 minus 2 infinity Ft e minus st dt. Now this becomes t. So this becomes t e minus st dt, which is minus 1 over s squared e minus st plus 1. Then it becomes 1 over s squared. So Laplace transform of t ut becomes 1 over s squared. So these are two examples of the Laplace transform. But for in this course, I not ask you to calculate this. Rather, I ask you to use this table to get dynamics of the system or to design a controller. So this is these are some frequently used the operations. So if you multiply k to a system, the output is k times Fs. So for example, the step function becomes k 1 over s. And then linearity theorem applies. The addition becomes a simple addition. And if you multiply some time decaying element, such as e minus at, it becomes f s plus a. And we also use these two and this integral a lot. This is because let's say the f is the position x. Then dx over dt is the velocity, which you will see a lot in the mechanical system. And then the Laplace transform of the dx over dt is nothing but s times x s minus f0 minus, which is this called initial condition. Similarly, Laplace transform d square x dt square becomes s squared. So instead of f, I plugged in x. xs minus s f0 minus, oops, instead of f, I need to use x. Minus x dot 0 minus, which will be initial condition again. And for the mechanical system such as spring, mass, and damper system, this will be 0 position and 0 velocity. And also you use this integral theorem a lot to design a controller with integrator. So please try to use this table. This table will be your friend, and calculate Laplace transform. So here are just some examples. So we want to take Laplace transform of the equation of motion, because we can get algebraic equation. Also, by taking Laplace transform, you can get a plant dynamics with input. In this case, can be ft, fs, and output. In this case, it will be xs. So you can have a block, a single block, by taking a Laplace transform. So let's get an equation of motion first using free body diagram. So this is there's a mass and F, and then there's a force due to spring, and the force due to damper. So this is a free body diagram. And the equation of motion can be mx double dot equals F minus kx minus bx dot. So we can arrange this, then we get a familiar equation. So you can get the solution of this xt, of course, using something like homogeneous solution and then particular solution approach. But it's much easier if you are using Laplace transform. Also, another benefit is that using this equation, it's very hard to make this kind of block diagram. How can you make this block diagram using this equation 1? But by taking Laplace transform, you can express this system with a simple input and output relationship. So let's take Laplace transform then. So it's very simple. So you can take L M x double dot px dot kx equals Laplace transform f, which becomes ms double dot px dot f. So now this is the time, then you can use these properties, the differential theorem. So this is exact the form. This is x2 dot, this is x dot. So you can use this. Let's say this is 2 and 3, minus 4. So you can plug in 2 and 3 to the equation 4. So let's plug in 2 and 3 to the equation 4. Then it becomes, I write to this side, m s squared xs, and it said 0 initial condition. So this part, for this case and this part, the yellow part becomes 0. So just having this becomes 0, this becomes 0. So it has only this part. And px dot, you can use this, p s xs. And again, the initial condition is 0. So it have only this part. And then k xs becomes fs. So this is the result of like after taking Laplace transform. Then we can arrange this equation. And xs becomes very simple. So after this, if you want, you can take inverse Laplace transform to get time domain solution. But more importantly, now you have a simple input and output relationship. So this whole part can be your plant, and the newer plant is derived by fs, and then the output will be xs. So then later, you can add actuator and controller. And you can use, and sensor. So then if you can use this functional block diagram actually to design your controller to have desired output, such as xs. So that's why you are using Laplace transform for this linear control system. It makes our life much easier and more intuitive. So if you want to review Laplace transform even more, please, you can go to this Khan Academy again. There's a Laplace transform tutorial. And if you have a time, I also recommend looking at this transfer function lecture by Dr. Brian Douglas. I found it also very useful. Okay, this is it for today. And thank you for watching this. Bye.